Hey guys, good morning or barely morning. We are going to talk today about differential equations. So I thought that we would start off with just a really basic lesson on how to solve differential equations and then how to create a graph that can represent all the possible solutions to a differential equation. So I've kind of given you guys just a lowdown on what differential equations are. So it's going to be an equation of a rate of change or an equation of a derivative. The solution is going to be the original equation. So obviously if you have a derivative and if you want a solution, then you solve this by integrating. And the method that we learn in this class is called separation of variables, but there's lots of methods. There's some really complicated differential equations out there that take a lot of work to solve. We don't really get into that in this class. Your solution after you integrate can be called a general solution if it involves C. If it involves a C, C could be any number, so it actually gives you an infinite number of possible solutions. Or it can be called a particular solution if you're given some initial condition that allows you to solve for C. So I just wanted to give you a differential equation and its solution for us to look at, just so you can kind of get an idea of what's really happening here. So we call this a first order differential equation because it just involves a first derivative. And so our differential equation is equal to negative 2y. Our solution to this differential equation is c times e to the negative 2x. So what I wanted to do is I wanted to show you guys the graph of all of the possible solutions. This is what we call a family of solutions. And this just represents, 8 of them. These could be shifted all the way up to positive infinity all the way down. They don't have to cross at whole numbers. They could cross anywhere depending on your value of c. And so we actually later are going to create what's called a slope field, which is going to give you an idea of all the possible solutions to your differential equation. We definitely couldn't graph all of them. We'd be here, for an infinite amount of time. But we'll graph some, and we can kind of use that to model what the differential equation would look like. So let's talk about the method that we use to solve differential equations, which is called separation of variables. Um, so what you're going to do, I just kind of have given you a list of steps. You're going to solve for dy dx or y prime first. Um, if I think it's easier that if you're given a y prime, you replace it with a dy dx, because what happens is you're going to move all your y's to the side with the dy dx, and then you're going to multiply both sides by dx. So you're going to end up with a bunch of y's on one side with a dy, and then a bunch of x's on one side with the dx. And then to solve, to get rid of the dy and the dx, you're going to integrate both sides. You only need one c when you integrate because, it's just a constant that represents any number. And then if you're given an initial condition, you're going to use it, plug in your x and y to solve for c, and then you always need to solve for y in the end, if possible, to get your solution. So let's practice some of these. So I've given you now the very first equation that I showed you, which was y prime is equal to negative 2y. So I don't have to solve for y prime because it's already solved for me. So I'm going to go ahead and rewrite this as dy dx is equal to negative 2y. And then I want to move my y over to the side with the dy dx. So I'm going to end up with 1 over y dy dx is equal to negative 2. And then I'm going to multiply both sides by dx. It doesn't matter that you don't have an x on the right-hand side. You can still integrate negative 2 dx and get a solution. So then we end up with, let me press this stuff down, sorry. So then we end up with 1 over y dy is equal to negative 2 dx. And now this looks a lot like an integration problem. So we're going to integrate both sides with respect to their given variable. The integral of 1 over y is the natural log of the absolute value of y. And this is going to be equal to, and I generally put my c on the side with my x, but it really doesn't matter, negative 2x. plus c. Now, I'm not given an initial condition in this problem, so I just want to solve for y, and that means I'm going to e it up. I'm going to rate both sides of my equation are going to become the exponent, and the base is going to be e. And once again, I need some more room. Oh, there we go. And so now this is going to cancel, right? And I'm just left with y. We don't need the absolute value anymore. And then I end up with e to the negative 2x. And then I'm going to rewrite this. I'm going to multiply it by e to the c. Now this notation looks, with this e to the c, looks kind of funny. Since c is really any number in the world, then we could call c e to the c, and it would mean the same thing. It's not going to matter when we solve for it, and it just makes everything look a little cleaner. So anytime you see e raised to the c power like that, you want to just write that as c, because any constant, I mean, e to the c is just a constant, just like c is. So we get that y is equal to c e to the negative 2x, which gives us the solution that you saw on the other page. So it's pretty easy, right? So let's take and let's try the next one. Oh, oops. Kind of running out of room. So let me move these way down. There we go. See if I can write a little smaller. Let me zoom in just a little bit. Oh, that's much better. All right. So we have 2y prime plus 5y equal to 4. So the first thing that I want to do is I want to solve for y prime. And the constant 2 in front really isn't going to make a difference. So I'm just going to say this is 2y prime is equal to 4 minus 5y. And then I have all my, oh, and then I'm going to rewrite this as dy dx, the y prime, right? So it's going to become 2 dy dx is equal to 4 minus 5y. Now, if I just add 5 to both sides, it's going to give me problems when I integrate, because I'm not going to have a dy to go with that 5y. The dy is only going to go with the 2 right here. So what I need to do is I need the dy and everything with a y in it to be multiplied together. So what is going to happen is I'm going to have to divide both sides by 4 minus 5y. So I'm going to end up with 2 over 4 minus 5y dy dx is equal to 1. And now I want to multiply both sides by dx. So I end up with 2 all over 4 minus 5y dy is equal to dx. And now I have my dy and my dx separated, that's why we call it separation of variables. I'm going to integrate both sides. I'm going to kind of pull up so I have some more room. Come up here. So this thing down here, I need to use a u sub on the left-hand side with the y's, because I see that I have 1 over a function involving y, which makes me think I'm going to use natural log, but it's not, the derivative of that's not 1. So I have to, do backwards chain rule, kind of. So my u is going to be 4 minus 5y. My du is going to be negative 5 dy. So then negative 1 over 5 du is equal to dy. So use all those same methods of integration that you guys already know to solve these. So this is going to become negative 1/5 times the integral of 2 over u. I guess I could have moved this 2. I like it better. It'll look cleaner if I do this. There we go, du. And this is equal to the integral of dx. You can think of this as the integral of 1. So now this is going to become negative 2 over 5 times natural log of the absolute value of u. I'm going to go ahead and plug back in. So this is going to be 4 minus 5y is equal to x plus c, because the integral of 1, or dx, is just x. So now before I e it up to get rid of the natural log and solve for y, I need to get rid of this negative 2/5. So I'm going to multiply both sides by negative 5 halves. And I'm just going to end up with a natural log absolute value of 4 minus 5y is equal to negative 5 halves x plus c. And now I don't have to worry about multiplying the negative 5 halves times the c. Same reason I gave before, e to the c can just be equal to c. Negative 5 halves c can just be equal to c. So now I can eat up. And so now I'm going to end up with 4 minus 5y is equal to, I'm going to go ahead, just like we did before, and take this c and move it down to the front. So this becomes c e to the negative 5 halves x. And now I need to solve for y. I don't have an initial condition, so I don't have to worry about solving for c. So I'm going to end up with, let's see, I'm going to subtract 4, and then I'm going to divide by negative 5. So I'm going to end up with y is equal to 4 minus c e to the negative 5 halves x all over 5. You could also write this, since c over 5 can just be equal to c, you could also write this, I'm going to move it this way, as y is equal to 4/5 minus c e to the negative 5 halves x. And that would be my general solution, right? So not bad. Just integration techniques y'all already know. Just have to set them up properly. All right, so now I've got a particular solution we're going to find. So I've given you guys an initial condition. And I have that dy dt is equal to 2 cosine t. This is pretty simple to solve for. I don't have anything on the right-hand side, so I'm just going to multiply both sides by dt. I don't have any other y's, so I get dy is equal to 2 cosine t dt. So then the integral, sorry, integrate both sides. And now this is just going to be y is equal to 2 sine t plus c. So now I'm going to plug in. So I've gotten to the point where I don't even need to solve for y because it's already solved for me. So now I just want to plug in my initial condition. T is going to be pi over 2 and y is going to be 1. So 1 is equal to 2 times the sine of pi over 2 plus c. Sine of pi over 2 is 1, right? So this becomes 1 is equal to 2 times 1 plus c. If I solve for c, I get that c is equal to negative 1. So now I want to always plug back in and write your entire solution. We want to write our particular solution. That can definitely get you points counted off. So we get that y is equal to 2 sine t minus 1. And there's my particular solution. Easy enough. So now let's talk about slope fields. So we want to create a graph that models all the possible solutions to our differential equations. So let's take a look. Oh, sorry. So slope field will approximate all the solutions. And so how you're going to do this is you're going to take your differential equation. You're not going to solve. You're just going to take the differential equation. And you're going to take and look at, you're going to have all these points on your graph. And then you're going to look at each point. You're going to find the x and y for that point, plug x and y into the equation, and then you're going to get a number. That number is going to represent the slope of the tangent line at that point. So then you're just going to take and you're going to make a little mark that is the approximate slope that you've gotten. You know, if it's 5, it's going to be really steep. If it's negative 5, it's also going to be steep but negative direction. If it's 0, it's going to be a horizontal line and so forth. And then you're just going to mark all these little lines. It's really simple, honestly, and students sometimes struggle with it because, I don't know, because I guess it seems kind of foreign to them. So let me zoom in just a little bit. So I want to create a slope field, and I've given myself a little blank graph here for negative 2x plus 2y. So I'm just going to start here at 0, 0. I see if I plug in 0, 0 for x and y, my dy dx is going to be equal to 0, so I'm just going to have a horizontal line there. Here, this is the point 0, 1. So I'm going to plug in 0 for x and 1 for y. So negative 2 times 0 plus 2 times 1 is equal to 2. And so I'm going to just draw a slope, what I think is about 2. It's always going to be really approximate. And then I'm just going to continue to fill in. This right here is going to be 0, 2. So that means x is going to be 0, y is going to be 2. So when I plug that in, negative 2 times 0 plus 2 times 2, that's going to be equal to 4. So it's going to give me an even steeper line. So here's 1, 0, right? So I'm going to plug in 1 for x and 0 for y, which is going to give me negative 2. And then you just continue to plug in. This would be 1, 1. So that's going to give me negative 2 times 1 plus 2 times 1, which is 0, and so forth. And you can kind of see patterns. I see that when x and y are equal, my slope's going to be 0, so I could just go through and plug in 0 for all the places where x and y are equal. And then you just go through and fill in the whole thing. So what I want you guys to do is I want you to pause the video, try to work out this problem. You'll have to use a calculator to approximate for sine x, and then come back and see how you did. All right, so I'm going to show you guys the solution. You should have something that looks pretty similar to negative cosine, because think about, that would be your solution if you solve this using separation of variables. All right, well, hope you guys had a good time, and I'll talk to y'all soon.